This video is going to be about nuclear energy. We're going to walk you through, or I'm going to walk you through how much energy is released in a radioactive decay series, as well as nuclear fission and nuclear fusion. As far as a lot more details, as far as the theory is concerned, I'd recommend that you read this little chapter here, separated in two different parts. Likewise, some other materials will be found on Friday, June 5th and Monday, June 8th. And then from there, I'm going to recommend I believe June the 11th. I don't have it on here, but on June 11th, there's going to be some more information about the nuclear fuel cycle, how nuclear reactors work, and how a nuclear weapon, nuclear bombs work, essentially. So that stuff I'll leave to you to read on your own. It's interesting reading. I'll post a few videos in the email about how that stuff works, but I do recommend that you go through that stuff. So without further ado, let's get busy. At the end of the 1800s, the very beginning of the 1900s, chemists kind of noticed a difference between the mass of atoms that were on elements in the periodic table. They found that there was a discrepancy with what they actually measured their atomic masses to be versus the mass of all the individual nucleons. So basically, I have 3 protons here, let's just call it lithium, even though it's just supposed to represent anything in general. If you look at lithium, and in the case here, this will be lithium 1, 2, 3, 4, lithium 7. It has 3 protons and 4 neutrons. If you add up all their individual masses compared to lithium that you find on the periodic table, just a solid lithium, this mass is greater than what the lithium that we find on the periodic table. So all the individual parts weigh more than the actual whole, which of course doesn't make sense. Law of conservation of matter says, well, that shouldn't happen. We shouldn't lose matter. But it was until 1905, Einstein wrote his paper, and then over time, over the next couple of years, it gained traction. It helped explain where that missing mass went. Einstein pointed out that there is a mass energy equivalence with his equation E is equal to mc squared. So of course, if you remember special relativity, it's E is total energy is equal to the gamma factor times mass times the speed of light squared. But if we're just talking about its rest energy, then that gamma factor factors down to basically 1, and it's not in there as far as its rest energy is concerned. So in this case, we're talking about the mass discrepancy, the missing mass. So that would be considered to be at rest. And so that missing mass is known as the nuclear mass defect. So compare that with, multiply that by the speed of light square, and that would be called your binding energy keeping the nucleus of an atom together. Because again, if you remember from your electricity section, your Coulombic force dictates that these positive charges, these protons, want nothing to do with each other. There should be a force pushing them apart. So the strong nuclear force provided by the binding energy is keeping them all together inside the nucleus. So that's where that missing mass went. It got converted into pure energy to hold a nucleus together. So that is the energy that is released in radioactive decay and nuclear fission and nuclear fusion. So to find the actual binding energy, you can just take any atom. So I'm going to take uranium-235 as an example, because this is a very popular atom when it comes to anything nuclear related. It's the main fuel source for most nuclear reactors around the world, and it is the favorite uranium of choice when it comes to making nuclear weapons. That's a topic for later. So if you look up uranium-235, it has a mass of, well, you can read that. I'm not going to say it out loud. And if you look at all the individual protons and neutrons and consider their masses in kilograms or atomic mass unit, you can pick and choose whichever one you want, and you move forward. If you multiply the proton mass in kilograms by 92 protons, because that's how many protons are in uranium, and take the neutron mass, multiply it by 143 neutrons, you'll get your values. And if you add the protons with the neutrons, you'll get a value that is slightly bigger than uranium-235 is naturally, 3.90 versus 3.93. So already you can see a difference. And then of course the rest just kind of really pinpoint that difference. So if you find the difference between those two masses, you can find your nuclear mass defect. this is the mass that's being converted into pure energy. So it's a slight difference. Now, you'll notice when you look at these numbers, oh, wow, there's 6 decimal places. Do you need all 6 of those decimal places? In some cases, probably not. In some cases, you will need them. Because if you notice, you lost your first 2 significant figures, the 3 and the 9, those went away. Sometimes you lose 4 or 5, sometimes even 6 significant figures in this process. So do keep all of them, at least for the few examples that you're going to work through on your own. Keep all of the decimal places. Sometimes you'll end up with more than you think you need, sometimes not. It depends on whether or not you do an alpha decay, beta decay, or nuclear fission or nuclear fusion. So just keep them all and try to have one standard as you do these problems. So that's the mass defect that you got, 3.0965 times 10 to the negative 27 kilograms. And then to find the binding energy, you would take that mass and just multiply it by the speed of light square. So speed of light square, of course, 3 times 10 to the 8 meters per second. If you square that, you end up with 9. I'll go over here, 9 times 10 to the 16 meters square per second square. So I rarely write down 3 times 10 to the 8. I just usually skip that and go 9 times 10 to the 16 meters square per second square if I'm doing it in my own notes. So if you multiply those two together, you end up with 2.779 basically times 10 to the negative 10 joules. Now that's a lot of energy to be released. Typically at the high school level, that's often good enough just to represent it in joules. It's hit and miss on, depending on where you go, whether or not you need to go further than this or just stop at joules. I'll go the next step and put it into electron volts. To convert into electron volts, again, this is just a benchmark for nuclear physicists, quantum mechanics, and chemists. They like the electron volts. You divide it by the 1.602 times 10 negative 19 joules for every electron volt, so that gets rid of the joules and gets you into that electron volt format. So in this case, you should have 1.70 times 10 to the 9 electron volts. And if you remember your metric prefixes, anytime you see times 10 to the 9, so a billion, you can just replace that scientific notation times 10 to the 9 with a giga. So this is often how you'd see it written as a giga electron volt. 1.74 giga electron volts is good enough as far as showing the binding energy, keeping the nucleus of the atom together of uranium-235. So if you're given a nuclear decay equation to find the mass defect, that would just be a matter of writing out the decay series and then take your parent mass, subtract your daughter masses plus whatever your ejected particle mass is. So you're going to have to be looking up a lot of masses. For that, inside your notes in Unit 5, you'll find page 104. On page 104, you will see this isotopes chart. So selected isotopes. I believe most of the stuff is fairly current. I know for a fact Xenon 140 is the most recent one because I forgot to match the font formatting when I pasted it in there. Give or take, of course, as this video gets old, as that table gets old, these masses update with more sophisticated measurements, but I'm going to stick with these ones, whatever's on here for now. If later on you look up some of these things and go, hey, polonium-214 is not that, it's something slightly different, well, I don't care, right? These are the masses you're going to use. They should be good enough to give you an idea of how to do what I'm trying to get you to do. So keep in mind, polonium also has like 30 something, I think it's 32 or 34 different isotopes. So if I ever say find the mass of polonium, don't just go to the periodic table and grab whatever mass is on the periodic table and multiply it by the conversion factor to get it into kilograms. You need this chart. Okay, at the very least, the answers in the back of the book are based off these numbers here. Alrighty, and as far as carbon 12 is concerned, that's not a typo. The atomic mass unit number was derived using carbon 12, so that's why it's a perfect 12. So just if you're lucky, that's one you'll use, but I don't think you will. So I'm just going to point out one more thing. Helium-4, you use this mass when it comes to alpha particles. Okay. If you ever have a beta particle, look up the mass. It's not on here. You'll just need the mass of electron from the main equation sheet from the start of the year. It should be on that thing in both kilogram form and atomic mass unit form. So here's our first question. How much energy is released in the alpha decay of polonium-214? So first off, show the alpha decay. Polonium-214, we know it's going to be an alpha decay. It says so in the question. So at the very least, we know it's going to be an alpha particle. And then figuring out what the daughter nucleus is, just a matter of working the math out. If I have 84 protons to start with, and 2 of them get lost, well, then that means I have 82 left over. And so you have 82 protons left over. You do the same thing for the atomic masses. 214 minus 4 gives us 210, right? And you determine what your element is by the number of protons. Use the atomic number to figure out the elements. Do not use the atomic mass. There's many different isotopes that have a mass of 210. So please, 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 please base whatever this number is, whatever this element is, on the atomic number. So number of protons. In this case, it's lead. Lead-210, also radioactive, also spits out alpha particles, but we're only showing the one decay here. So moving forward, to find the nuclear mass defect, we take the mass of our parent nucleus, so polonium, and we subtract the mass of our daughter nuclei. So that would be our lead-210 and the decay mass. So that's our alpha particle in this case. It's a bit easier if you just remember everything that's on the left-hand side, then subtract everything that's on the right-hand side. And so that's good enough. A bit easier way to remember it, left minus right. Okay, so that's what it looks like when you put it in symbol form. Normally I skip the step and just punch in the numbers. So again, the numbers come from this chart. Sometimes you might think you're reading lead-210, but you'll look at lead-210, but you'll write down the number for polonium-212 or polonium-208. It happens. So just try to be diligent. Sometimes I like to use a piece of paper and cover up everything except for whatever number I'm trying to write down. Because again, mistakes happen, and sometimes the mistakes are fairly simple, like just writing the wrong number down, or as you write a number down, you might call this number 213.959201, little things like that. Tend to drive you a little bonkers with trying to figure out why you get wrong answers by the time you're all said and done doing all this work. So be very diligent as you either write these on your piece of paper or punch them through a calculator, because there's lots of numbers involved, a lot of room to make mistakes. So these are the 2 numbers I'm taking, lead and polonium, and that's what I'm going to use for my alpha particle. I'll just zip through this because you don't need me to read these numbers out loud. So once you get to your mass defect, so that will be an atomic mass format, please put it into kilograms, multiply by the conversion factor. I'll leave it in purple, and so that'll give you the conversion in kilograms, 1.4 basically times 10 to the negative 29 kilograms. And from there, it's just a matter of calculating your energy using Einstein's mass energy equivalence. And that should give you an order of magnitude of 1.3 essentially times 10 to the negative 12 joules. So that seems like a very small amount of energy, but remember, this is for a single polonium-214. If you actually had a kilogram of this stuff, or even better yet, if you had a mole of this stuff, so that'd be 214 grams-ish of polonium. So if you would multiply this by Avogadro's number to represent 1 mole, you can pretty much see how that would be a large amount of energy. All right, so again, this is just per individual atom. So it seems like small until you remember to involve Avogadro's number. So convert it into electron volt format, because why not? You should be expected to know how to do both. And that should put you in the order of magnitude of 784,000 electron volts. I just kind of skipped to 3 sig figs at this point because I like the way this looks in 3 sig figs. Anyways, if you're in the 784,000 electron volts, you can just convert that into a 784 kilo electron volts. Okay, so that's how much energy is released when it comes to alpha decay. Alpha particles are not overly penetrating. They won't even go through your skin, but if you get alpha particles in your blood, you're basically dead. So that's where a lot of radioactive poisoning comes from, alpha decay inside your bloodstream. So that's pretty dangerous, but you can read the notes on that in on the class webpage. So that brings us to nuclear fission, nuclear fusion. Very often students have a hard time with these 2 words because they're very similar sounding words. Fission is the breaking apart of a large nuclei, so seen here on the left, and fusion is the coming together and of 2 smaller nuclei to build a larger nuclei. So fission breaks apart, fusion builds together. So that's kind of the 2 easiest ways to somewhat remember them. This is a very normal animation that you see when describing fission. Basically shows a neutron bombarding I don't know why, but whoever makes these almost always makes them so that protons are red, neutrons are blue. There's no color when we're at this level, but for whatever reason, most animations, most diagrams, most pictograms of the nucleus typically will make protons red. I don't know why, so there's no color. Anyways, so this is a neutron getting absorbed into the uranium-235. It causes fission, breakdown, and you end up with mess. And the chain reaction occurs. So in this case, we have 3 neutrons that are spat out according to this diagram, but we better do the math to make sure. So show the fission reaction of uranium-235 and barium-141 and krypton-92. Calculate the energy produced by this reaction. So to show the fission reaction, it looks like this. This is a fission reaction. Whatever our parent nucleus is will absorb a neutron. Okay, so when you combine these two together, you end up with uranium-236. I'm not going to write uranium-236 because this is how fission occurs. Uranium has to absorb it. It's going to produce barium and krypton, so we just write that out. So of course, as far as isotopes are concerned, 141 is the mass we use, 92 is the mass we use. Look up barium and krypton on the periodic table to find out barium is atomic number 56, krypton is atomic number 36, so you just have to look that up. And then the number of neutrons that spit out, well, the animation showed 3, but it's always best to make sure the math works out. Because again, it could be 1, it could be 2, it could be 3, it could be 4. It depends on a bunch of things. So in this case, here's what I do with the math. First of all, whatever I have here, I like to make sure that the number of the atomic number, the number of protons actually adds up properly on both sides. So 56 and 36, if you add them together, you do get 92. Whereas the atomic masses, 235 and 1 gives you 236. So that's where I typically write just above. And then I'll add those guys above. So 141 and 92 will give me 233. So I don't know how many neutrons are added yet, so I keep that ignored. So put an X there if you don't like the question mark. So from there, it's just, well, 236 is what I have for total atomic mass units. 233 are spoken for between these two guys, which means I'm missing 3 atomic mass units, which tells me I have 3 neutrons being spat out. So that animation was quite helpful in this regard. All right, so if you guys are doing your work on your own pieces of paper, you're not going to have an animation telling you how many neutrons you have ahead of time. So please keep that in mind when you're doing your fission reactions. So the nucleus breaks down, forms those products. So to find the mass defect, it's just a matter of figuring out everything that's on the left-hand side and subtract everything that's on the right-hand side. And that's basically what I have laid out here. Now, mathematically, there's often, every year someone goes, hey, wait a second, can't I just get rid of this and call this 2? And then, well, mathematically, I guess that kind of works out, but chemically it doesn't. If you don't add this neutron, fission doesn't happen. So do not do that in the nuclear reaction. Not a chemical reaction, it's a nuclear reaction. Down here, mathematically, if you wanted to get rid of this and only call that 2, that's fine. Right? I'm not going to be too picky about that. However, I will say that I typically like my math to match my nuclear reaction. Right? I like my math down here to reflect what I see up top. So I don't tend to take that shortcut. You guys are high school students. You do whatever makes you happy. I'm not going to read these numbers out, but as you can see, this is where mistakes will happen. You will probably write something down in backwards order, or else you'll muck something up in your calculator. Very often students forget to multiply the neutron mass by 3, right? They'll just plug this in as is, or by accident, they'll multiply this entire thing by 3. So there's a lot of chances for you to make mistakes when you're punching this through your calculator, okay? So if you can get this through your calculator, I often recommend that actually write this step out, add those together, write it down, figure that math out, write it down, because typically when you go to the next step, you can actually have a benchmark now. If you get wrong answers and you talk to your friend, they say, hey, well, I got it right. You can say, hey, well, what'd you get for this first number? And they read it out, it's the same thing, great. So you didn't make a mistake there. What'd you get for this number? Oh, this number is what's different. Then obviously you made a mistake adding these all together. Or who knows, maybe when you punch through your calculator, you got this right, you got that right, but you did this step somehow wrong. It's good just to get in touch with a friend and find out, okay, where did you make a mistake? Because odds are good, most of the time you just punch this into your calculator wrong. So in this case, for nuclear fission, you'll notice that my mass defect, I'm almost at 1 out here, right? It's 0.1, I'm almost at the 1's digit. So there's quite a large amount of mass that gets converted into energy. You still got 6 digits. It's not like the last couple examples we did. So there's more energy involved. Convert this into kilograms, and we have a large value in kilogram format, 3.089 times 10 to the negative 28 kilograms. Okay, work that through, find out the amount of energy, multiply by the speed of light square. So again, it's important that you recognize this has to be in kilograms, not atomic mass units. And you'll find in a typical fission reaction, you should end up with a value somewhere in the 10 to the 11 joules. Okay, so if you're at 10 to the 13 or 10 to the 12 or 10 to the 10 or 10 to the 9, you probably made a mistake somewhere up here. 10 to the 11 is where you should be as far as the joule value is concerned. If you convert it into electron volts, right, you'll find that you'll be in the hundreds of thousands of electron volts. Specifically, you'll be somewhere around 200, not thousands, I mean 1.7 times 10 to the 8 is hundreds of millions is what I meant to say, which means you are in the mega electron volt format. So in this case, you have 174 mega electron volts. Now, typically with a fission reaction, people are being general about it. They'll say that your typical fission reaction is going to be 200 mega electron volts. So you can just keep 200 in the back of your mind when you're doing these fission calculations. If you're somewhere within reason of 200 mega electron volts, then you probably did everything correctly. So that's a good benchmark just to keep in the back of your head. You get about 200 mega electron volts in a fission reaction. Yes, it'll mostly be a little bit less than that, but that's still a good benchmark to kind of remember, because there's a lot of work involved before you get to this step. So that was fission. This will be fusion. Example of the math of fusion says that the sun releases energy which gives our planet life. So nice. That energy comes from the fusion of two hydrogen isotopes, deuterium and tritium, into helium-4. Show this fusion reaction and calculate the energy released. So this is what the fusion reaction says. So I've got deuterium and tritium. I combine them together, so I'd write them out as two different hydrogens. Fair enough, deuterium has its own atomic symbol, so you could have wrote it out as like that, D with 2 on the top and 1 below. And I could have written, and if you look this up yourself, you might even notice that sometimes when people see this added together, they'll see that tritium has its own atomic symbol that's not on the periodic table. You can write those out that way if you want. I generally don't. I just stick with hydrogen. Oops. Oh, shouldn't have Control Z. Very sorry for that. 25 minutes in, I'm not going to stop the video here. Okay, very, very sorry. It's going to produce helium-4, so I write down helium-4. It doesn't say in the question that we have a neutron, so we have to just infer that. All right, we can do that by going, all right, well, we have 2 atomic mass units, 3 atomic mass units, add them together, we get 5. When you hear that you have helium-4, that specifically tells you that 4 of those 5 atomic mass units are spoken for, which means we have 1 atomic mass unit left over, and so therefore you'll just have to infer that is a neutron. If for whatever reason in a different, there's some fusion reactions where protons are emitted, sometimes beta particles are also emitted. If it gets into one of those more complex ones, you'll be told specifically what's happening. But if you're not told specifically, just assume it's a neutron. Okay, do the nuclear mass defect. It's no different than before. Left-hand side minus right-hand side. And I won't walk you through those numbers. Deuterium and tritium is on that chart on page, I believe I said 102. That's what they are there. Work your math through, you'll find that you'll actually get 0.01883 atomic mass units. Do the conversion into kilograms. I'm just going to zip through this quickly just to get to the end. Once you get your mass defect, multiply by the speed of light square, and you'll get an order of magnitude of times 10 less. So again, with fission, we got 10 to the negative 11. With fusion, we end up with 10 to the negative 12. So that's a smaller number, and yet I'll state that more energy is available here, and I'll explain that in a minute or two. But we're an order of magnitude about 10 times less. When you convert that into electron volt format, you'll find that you'll have roughly 17.6 million electron volts, or 1.76 times 10 to the 7 electron volts. Either way, that's good enough for me. If you can get a mega electron volt format, life is good. So with the fission reaction, we got almost a similar number. We got 174 mega electron volts. Now we get 17.6 mega electron volts. All right, so on paper, it looks like there's less energy with fusion. But if we look at their energy densities and compare the two, Fission, so when I say energy density, I'm referring to the amount of energy per atomic mass unit, not kilogram, atomic mass unit. If we actually look at the two, fission reactions typically give us somewhere around 150 to 200 mega electron volts. But just for simple math, I'm just going to call it about 200 mega electron volts. And if I take the typical three that are used for fission reactions are going to be some isotope of thorium, some isotope of uranium, and some isotope of plutonium. So if I just give a rough approximation and use the atomic mass unit from the fission example that we had, it's not too far off for the other two different types. 236 is about where we would be for atomic mass units. And now compare that to the fusion reaction of those two hydrogen isotopes. Right, we end up with somewhere a little less than 20 mega electron volts. Again, just a little bit of rounding there. 20 mega electron volts versus 200. Okay, so as far as energy is concerned, 200 is bigger than 20. But if you compare the mass that's involved in the fission process versus the mass involved in the fusion process, there is far more energy available in the fusion of smaller atoms than in the fission of larger atoms. And so this is the idea of why nuclear physicists are trying to make cold fusion reality, because there is more energy available per atomic mass unit, right? By a much larger factor than just by a multiple of 4. This is actually somewhere around like 0.6 or 0.7 mega electron volts. And this is, I guess, closer to about 3.8 or something. I can't quite remember what it was. So there, either way, there's more energy involved here as far as our atomic mass unit is concerned. Plus, there's the abundance of deuterium and tritium found just naturally around Earth is far greater than the abundance of uranium, which is what we're typically using for fission. Thorium, there's lots of thorium involved, but that's not as common of a fuel, if you will, for fission. Plutonium is man-made, so you can't just go and find that naturally on Earth. So the only problem with fusion on Earth, when we try to do this in a lab, is it requires somewhere around 40 million degrees Celsius or 40 million Kelvin, because at that point, when you're in the millions of temperature measurements, Celsius and Kelvin are basically the same. And you have to get the temperatures up to somewhere around 40 million degrees Celsius just to break the Coulomb barrier. So that force equation that we did in our fields unit before you can get the two protons to go together in the same nucleus. So that requires a large amount of energy just to bring it up to that ability. So we haven't quite figured that out yet. When we do fusion in our labs, at the moment we use more energy than we output. Requires more input energy than output due to, well, second law of thermodynamics. There's always going to be some kind of lost energy. So we're still working on that. Cold fusion would just bring the temperatures down, be able to do fusion, but at temperatures somewhere around the hundreds of thousands of degrees Celsius. So that's still pretty hot, but it's cold in comparison to the millions of degrees Celsius. So I can see I broke the 30-minute mark. Sorry about that. I'm going to stop the video here because everything else you can just pretty much read about, or if you have other questions about how nuclear weapons work or how a nuclear power station works, you can send me an email and I'll walk you through that as best as I can. But otherwise, stick with the reading materials I posted online and some of the videos I'm going to put either down below in the description or in the email that I'm sending to you, which I'll do right away. All right, well, thanks for watching if you made it this far.